is the equivalence, is the notion of embeddings which induce the same norm on K. And you see the point is complex conjugation is an isomorphism from the complex numbers to itself, which is norm preserving. The norm of Z and of Z bar is the same. So if I've got a map from K into the complexes, and then I apply complex conjugation, I get a different map from K into the complexes maybe, but it induces the same norm. So I want those different maps to be the same place. So if sigma is complex, you see if sigma is real valued, then C composed with sigma is just sigma again. But if sigma is not, then C composed with sigma is a different embedding. So this is an equivalence relation on the set of all embeddings, and the equivalence classes have all got size 1 or 2. The size 1 equivalence classes are maps from K to the reals. The size 2 equivalence classes are maps from K to the complexes. The image does not land in the reals, but they're identified with the complex conjugate. So if you wanted to do kind of concrete mathematics, you could choose a representative in each equivalence class. So for each complex place, you could have a preferred sigma from K to the complexes. I think a well-chosen example will perhaps illustrate this in a completely different way. The idea is I want to consider K infinity is K is kind of the direct sum, as it were. It's the direct sum of KV for V a place, V an infinite place. And I also wrote this as a product because this is a finite thing. People write V divides infinity for an infinite place there. And KV is if sigma is real, KV is just the reals. And if V is one of these pairs of complex places, then KV is isomorphic to the complexes, but we don't quite know how. And as I say, let me start with a well-chosen example. Let's just do an example. So this turns out that it equals K tensor QR. That's the. Let me show you this happening. I'm going to prove this by. I'm going to both prove this and motivate the definition of everything just by one well-chosen example. So let's do an example. Let's do the simplest number field about which we know nothing about global Langlands for GL2. So let's do K. K is Q cube root of 2. Right? Now, you might know that for elliptic curves over CM or totally real fields, we can maybe prove potential modularity, and there are all sorts of fabulous statements about global Langlands conjectures proofs for GLN over an arbitrary totally real or CM field. Well, this field is neither totally real nor CM, and it's pretty simple, and we know very, very little about the global Langlands philosophy, even for GL2 for this field, right? Given a random elliptic curve over that field, the chances that we're going to be proving it modular anytime soon are pretty much zero, I guess. Yeah, I think that's true. This is a really, really, from the point of view of this fancy global Langlands stuff, we just don't have the tools. This field is beyond our reach. And let me show you what K infinity is. K infinity is just K. Here's this is the cool definition. That's the swanky definition. Not that any of you know what swanky means. But we have to try to translate this into a sensible definition. So this is K. We can figure this out, right? This is not difficult. This is not difficult to figure out. Let me show you how to figure this out. Because if you think about Q cube root of 2, that's Q. What does Q cube root of 2 mean? It means we take some random new variable x, which is secretly our cube root of 2, and then we quotient out by the polynomial x cubed minus 2. This polynomial is irreducible over Q, right? By Eisenstein's criterion, if you like. Or if you like, the local extension Q2 of the cube root of 2 must have degree at least 3, because the valuation has gone up by a factor of 3. So even the local extension's got degree 3, so the global extension must have to have degree at least 3, so this must be irreducible. That's the proof of Eisenstein's criterion. So there's Q of x modulo x cubed minus 2, that's K, and I need to tensor this with R. And it's really easy. I'm tensoring over Q, and it's really easy to do that tensor now because Q, when you just change the Q to an R. So this is Rx modulo x cubed minus 2. right? That's what k infinity is. And now x cubed minus 2 used to be irreducible over q, but over the reals that's not irreducible anymore because it's got degree 3, and irreducible polynomials over the reals have got degree 1 or 2. This polynomial's got a root in the reals. So let's let the three roots, let's give names to the three roots, right? Let's say the roots of x cubed minus 2 in C, what are they? Well, there's a real one. Let's say alpha. There's the real cube root of 2 in the reals, the positive real cube root of 2. And then there's two more, right? There's alpha times omega and alpha times omega squared. There's three cube roots of 2, and two of them are complex, and the other two are complex conjugates. So let me call them Z and Z bar. Z is that, let's call it W. I want to think of there, W and W bar, the other two roots. Right? So W, whatever. W is kind of alpha times e to the 2 pi I over 3. And W bar is alpha times e to the 4 pi over 3. Okay? So those are my three roots. And you see we've got the reals here, so those three roots are going to play two different roles, right? That's some definitions. Now let me go back to infinity. So k infinity is now r of x modulo a polynomial that factors. Well, we can't use w and w bar because they're not in the reals, but we can certainly use alpha. So it's x minus alpha times whatever's left. I need to do x cubed minus 2 divided by x minus alpha. And this is like x cubed minus alpha cubed over x minus alpha. So this is x squared plus alpha x plus alpha squared. Right? And this must be the irreducible quadratic polynomial, irreducible over the reals, that has these two roots as complex roots, right? So it's r of x modulo the product of two polynomials. And both of these polynomials are irreducible, right? These are irreducible, and these are co-prime. So by the Chinese remainder theorem, because they're irreducible and distinct, right? So they must be co-prime. So by the Chinese remainder theorem, so by the fancy version of the Chinese remainder theorem, to give a number modulo x times y is the same as to give a number modulo x and a number modulo y. The proof of that generalizes to showing things like this. So this is going to be r of x modulo x minus alpha, that thing there, cross r of x modulo x squared plus alpha x plus alpha squared. Right? So k infinity, I've figured out what k infinity is. I've figured out what k tensor r is, and I'm telling you that that's kind of a swanky definition of k infinity. So this is silly, right? We've thrown in a new variable x, and we've proceeded to instantly then decree that that variable is alpha. So this is just canonically the reals, right? It's canonically the reals, and we've decided that x had become alpha. X is cube root of 2, right? And so what we're saying here is we're saying, let's think of a map from k to the reals, and let's send the cube root of 2 to alpha. Remember, this is quite an abstract cube root of 2. It doesn't really make sense to say if this cube root of 2 is real or non-real. This is quite an abstract, this is just a random new variable whose cube is 2. So it doesn't particularly have to decide if it's real or non-real. Right? You know, I can just abstractly think of this as q of x modulo x cubed minus 2. Right? I'm going to define that to be this, and then it doesn't make sense to talk about whether alpha is real or not. But here, alpha has really x has made a choice to be alpha. So this is r. And now here, this is r of x modulo an irreducible degree 2 polynomial with no real roots, right? Because the roots of it are w and w bar. So this is definitely irreducible degree 2. And if we throw in a root, e.g. w or w bar, then we'll get, this is a non-real thing, right? This is the point, right? W bar are not in the reals. So we throw one of them in and we get the complexes. So this is isomorphic to the complexes. Right? But it's not equal to the complexes, because if I want to make it equal to the complexes, I'm going to have to decide where x is going. Right? This has got an element called x. I mean, I suppose it's really literally called the coset of x modulo this polynomial. But let me call it x. Where's x going? Right? There's two choices. X can go to w, or it can go to w bar. And those two choices give two different isomorphisms. So I'm really reluctant to say that this is... I don't really want to choose. you see. And what's happening here is I've got sigma from k to c, sigma of the cube root of 2 is w, and then I've got c composed with sigma, and that's saying to the cube root of 2 to w bar, and I'm not really too fussed about which one I choose. To be quite honest, I'm quite happy with it like this, right? I just want to take this. I'm quite happy with that field being isomorphic to the complex numbers, but in a way that I'm not particularly going to ascribe right now, you see. So there's k, this is kv, for v equals sigma from k to the reals, sigma of the cube root of 2 is alpha, right? So that's what kv looks like. It's canonically the reals. And this, that's k, that's k whatever, v primed, where v primed corresponds to this. So there are times in my life when I worry about whether I should be kind of stressing about this sort of thing. But it's just sometimes it's useful to know that that some of these completions are kind of non-canonically the complex numbers. It just helped me. One or 2 points in my life, this point of view has helped me. That's all I'm going to say about infinite places. So now I want to do the analogous thing with p-adic places. I want to do k tensor q qp for all primes p at once and then put everything together. And you do that and you get the Adeles. Right, so there's the real Adeles. Right, so here's the definition. The big key definition of the week. Definition, the Adeles. Right, so K a number field. Okay, so then the idea is, so K contains OK, right? And that's got infinitely many maximal ideals, right? There, they tend to be called P. And I sometimes call them finite places, right? It's just another word for it. It's just another word for it. And now, given K and a finite place, I can complete, right? K and P. The data K and P goes to the completion, KP, and that contains OKP, right? That's sort of sensible. So if K is the rationals and P is just a null prime number, then that's the p-adic numbers, that's the p-adic integers. But remember, if K is the rationals, then there's infinitely many prime numbers. And similarly, for K, a general number field, there's infinitely many prime ideals because there's at least one above every null prime number. So I want to do all of these, just like I somehow looked at all the infinite places, I now want to look at all the finite places. But there's infinitely many finite places, so there's a subtlety, right? So let me define the finite Adeles, A, K, F, right? That means the finite Adeles of K. And it's not quite you see, with the infinite places, I just took the product of all of them. There was finitely many infinite places. Let's just take the product. You see here what's happened. There were two infinite places. There was a real one and a complex one, and I just ended up with a copy of the reals and a copy of the something isomorphic to the complexes. So I want to do the same for the p-adic places, these finite places, but there's infinitely many. So AKF is actually a subset of the natural definition, which is the product over all P, a finite place, where a finite place is just the same as a maximal ideal of OK, KP. Right? That's not the Adeles. This is too big. So this right-hand side is too big. Everyone always says too big. I actually know a rigorous, it took me a while to discover this, but if you ever read Tate's thesis, you'll see that a crucial role is played by a Haar measure, and Haar measures work for, this is irrelevant, Haar measures work for locally compact groups, and this is not locally compact, right? And the reason it's not locally compact, all the factors are locally compact, but when you take a product of infinitely many factors, you have problems because kind of open sets in the infinite product always tend to involve this entire full big set for all but finitely many P. So every open set is necessarily has to have infinitely many kind of non-compact things in it. So this is not local. When people say it's too big, one way of interpreting that is it's not locally compact. So I'm going to write down a subset of this space that will be locally compact, although I won't ever really explicitly mention it or use it. If you read Tate's thesis, you might need to understand how to do global harm measures on this space, and then you will need local compactness. But let's not worry about that. The point is, what I want to have is something sufficiently big that it contains. I do want this to contain every element of K, and so this is the observation. If I take a random element of K, then it's certainly there's a map from K to KP for every P. So I take a random element of K. It's certainly in this right-hand side. But I can do better than that. If I take a random element of K, then it's a numerator over denominator, and the denominator only has finitely many primes involved in its prime factorization. So I only need to take the full KP for a finite set of P, and for the rest of them I could just use the integers. Right? A random element of K will be integral at all but finitely many places. So I could get away with the product of OP as long as I just allowed a finite number of places to have denominators. So that's what the Adeles is. So the finite Adeles equals the set of xp, so p running through the finite places. So it's the elements xp in this infinite product of kp such that xp is actually in the integers of kp for all but finitely many p. Right? So you could rewrite that as saying you want. Let me show you another way that you can write that, which will confuse things a little. Let me just introduce. If I try to introduce notation for the bad set of finite primes, then there's potential confusion, right? So let me just do it. Let's just do it right now, once and for all, just to dispel any confusion. So it's xp. So xp is in one of these local fields, in these product over p of kp, such that there exists some finite set S, exists S finite, a finite set of bad p, with the property that xp is in OP for all p not in this bad set. So the problem with writing the definition like that, which is how you sometimes see it in some books, is that you then have to, there's an S here and there's no S on this side of the definition. And it's just, you have to kind of, what does this like, so it's the idea I pick a finite set of bad places and then I make this construction using that finite set S. And that's not how it works. So when you write it this way, you have to remember S can depend on the choice xp. So it's a bit weird because you know that there's a finite set with some properties, and what is the finite set? Well, the answer is, well, first of all, you have to give me the element, and then I'll tell you whether the finite set exists or not to see if we're in. So if you fix a finite set, then you end up defining something called AKFS. And then you can define AKF as the union over all finite sets S of AKFS. So there would be another way of doing it. So I kind of like this best. So elements in, it's just like K, right? Elements in K, they're elements in OK, except I'm allowing finitely many primes in the denominator. Right? It's the same sort of phenomenon. But I'm not saying which ones. I'll let you have any finite. As long as it's finite, you can have any finite bad set. So there's the definition of the finite Adeles. That is clearly a ring. AKF is clearly a ring simply under pointwise addition and multiplication, plus and times. Right? It's not going to be very good topologically. You can't imagine kind of taking limits, because if you took more and more elements of this with S getting bigger and worse and worse and worse, then maybe the limit would have S infinite, right? So maybe you've got to be careful. What I'm suggesting is perhaps it might not be complete with respect to any sane metric or something. even though it's a product of complete things? I don't know. It's clearly a ring. Let's not worry about whether it's complete. It's clearly a ring because I can do pointwise addition, I can do pointwise multiplication. I take two random elements, they've both got a bad set associated to them. The bad sets might be different, but we just let the new bad set be the union, right? So we can add, we can subtract. We've got 0 and we've got 1, because 0 is the thing that's 0 everywhere. That's all right, S can be empty. 1, we can be 1 everywhere. And in fact, more generally, there's a map, right? There's a map from K to AKF. A diagonal embedding. There, that's kind of cool. Because you see, the idea is if I've got some random element of K, I can write, this is lambda, this is A over B, right? With A and B in OK, and B not 0, right? And so there's only finitely many. Just let S be the set of primes P of K, such that P divides B. Right, there's your problematic primes. These are exactly the P finite places. Curly P, I'm sick of calling them finite places. If I write curly P, I mean a finite place. I mean exactly what I've used curly P for the entire course. S is the P of K such that P divides B equals the P such that the p-adic valuation of lambda is less than 0. Right? And that's finite. And so away from that finite set, this element lambda is an integer, right? The p-adic valuation of lambda will be greater than or equal to 0. In fact, I guess if lambda is non-zero, then both A and B will be non-zero. So for all but finite, if lambda is non-zero, then for all but finitely many places P, V of P lambda will actually equal 0, right? Just imagine a rational number, random number over random number, for any prime that doesn't divide the numerator or denominator. The p-adic valuation of lambda will be 0. So K lives in AKF, the diagonal embedding. So AKF is a really unwieldy object. I'm going to give it a topology. Let's topologize. Let's topologize AKF by saying there's this random finite set of places where I'm allowed to be a little bit denominatory. Let's just imagine that set is empty temporarily. If that set's empty, then XP would be in OP for all P and S. For all P. So AKF seems to have this canonical subring, that the subring, the product of all primes P of OP, there, that's a subring of AKF. That's the set for which S can be empty. And that's a pretty sensible subring. These are compact. Product of compact spaces is compact. So that's going to be a nice compact open neighborhood of 0 if it's got the normal topology and if it's open. So let's just demand that. Let's say the subring is open with the usual topology. You see, so I'm defining the topology on a subring. This just has a product topology. This has a product topology, and it's a nice topology. It's a compact thing. And if I demand that this is open in here, then I've told you what a basis of open neighborhoods of 0 looks like. And now to get a basis of open neighborhoods of any element of this ring, I just take the element of the ring and I add this set, and I've now got some big neighborhood of my original point that's isomorphic to this set, and I'll keep the topology. So there we go. That turns out to be a definition of the topology on the Adeles. I guess we need to kind of get the hang of this. But still. So there's AKF, there's the finite Adeles, and now I can finally define the Adeles. I'll tell you notation. Let me just give you notation. AKF it's sometimes written. There's there's a quite bad notation called restricted product. It's sometimes written AKF is the restricted product of KP, right? See, that doesn't. Restricted product means you don't consider everything. You have to. There's some condition, and the condition is the thing I've written down. But you see, you can't really see. Do you see that apostrophe is doing a lot of work here, right? That apostrophe contains some implicit assumptions that all but finitely many of the topological spaces involved here have got canonical open subspaces, and that we're demanding that my element has to be in this canonical open subspace for all but finitely many P, right? So there's a pretty overloaded apostrophe. It's pronounced restricted product. And it's quite a good way of, if you want to, if you're actively trying to confuse people, it's a very good piece of notation to use. So there's restricted products. I guess I could use it right now in the next definition. So let's define the Adeles. I've defined the finite Adeles, and I've defined K infinity, which is the infinite Adeles. So now I can just define the product. The Adeles of K. Of the finite Adeles across the infinite Adeles. There you go. So of course that's just equals the product over V, all places of KV, restricted, right? So there you go. I could have just written that down, could have put it at the beginning, we would have had 15 minutes of your life gone. I could have, there's the definition. I could have put it all in that apostrophe. You see, there's finite places, there's infinite places, and a place is by definition either a finite place or an infinite place. So this is the product over the infinite places. This is the restricted product over the finite places. So we've got the product over all places. So this gets a product topology. Somebody asked me yesterday if this could be given the structure of a manifold. I thought it was quite a good question. Because you see, K infinity is clearly a real manifold, right? Because it's just isomorphic to R to the n. So it'd be nice to talk about smooth functions. We could talk about smooth functions on K infinity. But this is a really locally pro-finite thing, right? This AKF, it contains as an open subring this product of P, and that's a pro-finite topological group, right? So it's not really the kind of thing that you'd normally do analysis on somehow. But you could define a function on this pro-finite thing to be smooth if it's locally constant, and you could define a function on the infinite thing to be smooth if it's C infinity. And so even though this might not be a manifold, I still have a good notion of a smooth function. So we could talk about smooth functions on the Adeles. So there's the Adeles. So my memory of first learning about the Adeles was I found this definition really rather unwieldy, and also somehow I could see that there was never going to be a point to it, right? Because there's too much information. But it's kind of it's surprising that this ring can play any role in some sense. Let me give you an analog of what this ring looks like. Let's say we're really interested in meromorphic. Let's say we're interested in kind of, meromorphic functions on projective one space, right? That would kind of like C of T, if T is my parameter. Meromorphic functions on projective one space over the complexes. That's somehow reasonable. That's a reasonable field to be interested in. It does have the feeling. It does have the feeling of being a one-dimensional field, like K, right? K is a number field. K contains OK. This is a ring. This is some kind of canonical integral structure on K. And this ring is one-dimensional in the sense of ring theory, right? It's an integral domain. 0 is a prime ideal, and then any other prime ideal is maximal. So you get chains of prime ideals. They go 0 to maximal ideal to the whole ring. And that just means it's got dimension 1. That's how dimension works in ring theory. So C of T contains C square brackets T, and this ring is the same. This ring has the same property. This is a one dimension. This is meromorphic functions that only have poles at infinity. And And this is the same story. This is a one-dimensional ring. Because you have the 0 ideal, and then all the other ideals are generated by t minus lambda, all the other prime ideals, and they're all maximal. So there looks like some formal similarity. And if I've got C of t here, if that's my field K, then I want to look at the Adeles of K, and what I'm doing is I want to look at every single complex number. So now V is a complex number. So I could look at this meromorphic function and its behavior near V, and I could take a power series expansion, right? So I could kind of look at the Taylor series. I could look at the power series expansion of this function near the point V. So if you think about it, for any random polynomial t, I take some, an element of this thing here is just a ratio of polynomials, p of t over q of t, right? And I could substitute V as an explicit complex number now, so I could substitute t minus, I could write this as h of t minus V over j of t minus V, where h and j are now new polynomials, and pretend t of V is a variable, and now expand everything out, and I could get a power series for my random meromorphic function about the point t equals V. And that power series will live in this double bracketed thing. But if I take a random function here, it'll only have finitely many poles, right? So K actually lives in not just this, it lives in the restricted version of this, where I'm taking the restricted product over K over C square brackets T minus V. These are meromorphic functions which happen to be holomorphic in a very small, holomorphic at V, and hence in a very small neighborhood of V. So that's what I'm doing. I'm taking a global function, and I'm concocting a gigantic space that contains all the information about the function's behavior locally, but it contains it in a very fluid way, in the sense that I can now start modifying local behavior at one place without changing it at any other place. So that's the power that the Adeles are giving you somehow. This is a completely analogous construction, you understand. And in fact, when you do class, I mean, if I were doing this course properly, and I wasn't talking about number fields, I should really be talking about global fields. And an example of a global field would be a function, something like this, or a finite extension of this. If I take a finite extension of that, that's called a global field, and all of the global class field theory and Langlands philosophy, one can state it in that situation. The problem is there's extra technicalities, one has to worry about separate extensions, and the other problem is the global Langlands conjectures have essentially all been proved by Laforgue and Laforgue. There's two Laforgues, and they've kind of done a huge amount of work on both the local and global conjectures. So it's a kind of extra work to carry this function field story around with you, and then at the end of the day you say, oh, and by the way, it's all been proved, and the proof uses moduli spaces of Stukas, and there's an entire week gone somehow trying to explain what a Stuka is. Believe me, I've tried. I think Rebecca was probably there. I've lost Rebecca. Did you watch me ever explain what a Stuka was once? Can't remember if you had to endure it. So anyway, they're kind of function field analogues of elliptic curves, but they're not anything like elliptic curves, that's for sure. That's all I know. Right, so there's the Adeles. Why the heck have I introduced such a crazy thing? There's global class field theory coming in a minute, and that's going to be this. I've written here. Let's do an example. Let's do A of Q. Let's just prove some lemmas. It's not even an example. Oh, I'll tell you what. Here's a remark. Just as K infinity is K tensored over Q R, which is K tensored over Q infinity. Think about it. Q infinity is the reals, right? There's only one embedding from Q into R, and it's real, and it's that. We have AKF equals K tensored over Q AQF, and AK is K tensored over Q AQ. Right? These are slightly tricky, but it's nice to know that in fact somehow the fundamental object is the Adeles of Q, and then we can get the Adeles of K by just bootstrapping up. So there's quite a tricky exercise actually. I know it's tricky because I always think it's obvious, and then occasionally this ends up coming up in some. I've seen people struggle with this, and that's what reminds me. It's less obvious than I think. I look at that and I always think, yeah, that's just the definition. But actually, when you start writing down the details, it can get a bit painful. Blah, 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 blah. Oh, so while we're here, I may as well tell you, no, let's do this. This was supposed to be justification of the fact that if we understand AQ, then we're at least part way to understanding AK. Let's just do an example. Quick example. Here's a lemma. Is that AQ is Q. Sorry, the finite Adeles. AQF is Q plus. What do I mean by this? A plus product over P of ZP. I.e. for all XP in AQF. Remember, did someone say something? AQF is the finite Adeles of Q, so what does that literally mean? An element of AQF is a huge amount of data. It's XP. For each prime number P, it's a number, right? So for all P prime, I have XP just in the p-adic numbers in QP. And then there's a catch, right? XP has to be in ZP for almost all P. I hate using this phrase, and I wish there was good abbreviation for it. Almost all P means all but finitely many. It means different things to different people, right? To the measure theorists in my department, it means for all P outside a set of measures 0. And there are measures on the prime numbers. You can kind of like look at the number of prime numbers less than x with a certain property and divide it by all the prime numbers, the number of primes less than x. And if that thing's tending to 0, you could argue that that set of primes has got measure 0, but it might be infinite. So I don't like using this phrase at all. So I'm going to define almost all P. Let me make a local definition for this course. Almost all means all but finitely many. Forget that definition when you leave this room, because other people in your universities might mean other things by it. So what's this lemma say? This lemma says I've got an element of the finite Adeles, and I'm claiming that I can write it for all P of this form. There exists some lambda rational, right? Remember, the rationals are embedded, right? There's a weird map. This is lambda goes to lambda, 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 right? Got a random rational number. I just pretend it's a 2-adic number, then I pretend it's a 3-adic number, then I pretend it's a 5-adic number, and that will land in the Adeles. There exists a lambda in Q and mu in the product of P ZP such that x equals lambda plus mu, right? I've called it XP, I could just call it x. That's what that means, right? So basically it means I've got a random finite Adele. This is some random p-adic number for every prime P, totally unrelated. All we know is some integrality constraint, and now I'm claiming that I can find one rational number that's the same at every prime, so that if I remove this rational number, I can fix all the poles, right? Because what I'm trying to say, this is holomorphic functions, right? The product of CT minus V, this is functions on affine 1 space that don't have any poles anywhere, because I've got a power series expansion at every point V that's holomorphic, right? 2 square brackets means holomorphic. 2 round brackets means I'm allowed poles. So this is holomorphic functions. This says if I've got a random Adele, I can change it by a globally meromorphic function and get something which is holomorphic everywhere. So you see, this is a Riemann-Roch type problem, right? I've got a collection of local functions everywhere, and I need to find a global function that has the same poles. Okay? I'm dressing this up in a geometric language because I think it's a helpful point of view. But of course, when I write the proof, I'm going to have to prove something. I'm going to have to do something algebraically. So how would you do that, right? Let's think about it geometrically. Let's say I've got a meromorphic function on projective 1 space. No, let's not say that. Let's say I've got an x. Let's say I've got, for every single point on the complex numbers, I've got some power series, and for finitely many of those points, that power series is meromorphic, and it has some kind of annoying tail, right? So I could write down that tail explicitly somehow, and maybe that tail, like, I'm not worried about the infinite converging business. If I just write down the tail, the bad meromorphic part, then that tail is just a finite sum, so it will probably be a global holomorphic function. This is great. So okay, I'm going to fix. Yeah, I know what to do now. If I've got a tail here, I can fix it. I can write down a global meromorphic function that only has a pole at that one point, and the pole is behaving in exactly the bad way that I want to cancel out. So I know what I'm going to do. So here's the idea. Remember, so by definition, there exists some S, right, finite set, such that xp is in zp for all p not in S. Right? And now my game, you see what for mu, that corresponding value of S is empty, right? Mu, I'm well behaved everywhere. But the problem is for a general X, I'm badly behaved at a certain finite set of points, and I need to use my lambda to fix those finite set of points. Okay, so I've got XP and ZP. So let's just choose, I'm going to prove this by induction on S, right? The idea is induction on S. On the size of S, right? If S is empty, we're done, right? Just lambda can be 0, right? And mu can be x. Because that's exactly what mu is. Mu is a value of the Adeles for which S is empty, right? And now what's the inductive step? I need to kind of, given a random problematic x with a finite S that isn't empty, I need to figure out how to make S smaller, right? So general X, just choose P, choose some problematic prime P in S, and now let's look at XP, right? And XP is in QP, right? It's not in ZP. That's really irritating. So I can write XP explicitly, right? It's A negative n, P to the minus n, add A 1 minus n, P to the 1 minus n, add dot dot dot, add A minus 1, P to the minus 1, add A 0, add A 1P, add dot dot dot, right? This is a finite dot dot dot. This is the finite tail. This goes on forever. This is a p-adic number, right? I can't make that sum converge in the rationals, but this is the, of course, so I'm using this standard convention, right? Every p-adic number has got a p-adic expansion with respect to these p-adic digits, and there's a lot of flexibility with regard to these p-adic digits, but let me just choose these as a sensible choice. So there's my meromorphic function defined in a neighborhood of a point. The point is the prime number p, yeah? The Riemann surface I'm working with is spec z, right? It's that smooth affine curve whose points are prime numbers. So I've got this meromorphic, this is a local thing. This is a meromorphic behavior at some point. And now this is my tail, right? This is my problem. And let's just define kind of lambda is a minus n, p to the minus n, plus dot dot dot, plus a minus 1, p to the minus 1, right? And that's some random number divided by a big power of p. Okay? So look at that. So you see, this is this function is holomorphic at all points on my Riemann surface other than this point here, p. I'm going to just say that I'm going to say it using the language of functions, but what I'll write is kind of rigorous arithmetic, right? So you see the R-adic valuation of lambda is going to be at least 0 for all R not P. Okay, the only problematic prime in lambda, the only thing stopping lambda from being an integer is the fact that there's one prime P in the denominator. Okay, so if I look at x minus lambda, if x used to be well behaved, if xr was in zr, then when I take away lambda, it's still going to be in zr, you see, for r not p. So the idea is, I take away, this is a global holomorphic function that only has a pole at one point, right? This is some explicit polynomial divided by t minus v to some big power n. right? If I have a polynomial in t divided by t minus v to the power n, that function is holomorphic on the whole affine line, on the whole complex numbers, apart from that point t equals v, where it's got a well-defined pole, and this polynomial here, I can rig the polynomial to make exactly the non-holomorphic part be exactly this polynomial. So that's what I've done with lambda, and so now I just look at x minus lambda. This is now yp, right? And now what's the bad set? Bad set for y, i.e. the things for which, bad set for y, the stuff I mean for yr. yr is not in ZR. What's the bad set for y? Is S, except I've removed p, right? It's got smaller than S. So I'm done by induction, right? So there's how that proof goes. So you see, this lambda fixed the problems at 1', and then if S is not empty yet, I just keep going. I build global meromorphic functions which are holomorphic everywhere apart from a point, and at that point, they're exactly mimicking the bad local behavior that we're seeing on our Adele, sorry. So that's the proof of the lemma. Normally you get a box. Oh, there's the box. I'll be using that lemma later, because this part of the course has actually had some thought going into it. Blah, 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 blah. That's done that. I think you can prove it for general K, but life's a bit harder, because prove for a general number field, you have issues with non-principal primes. But I decided that you could resolve the issues. But I decided it was just not really worth, it's a tricky exercise. AK is K plus product of OK, P. That's, again, a challenging exercise. So people that want to understand the Adeles properly, because the problem is if P is a non-principal prime, you have to think a little bit more carefully. Yeah, you can't do n divided by p to the n, but when you think about it, p to the n, if you know this is a class groups are finite, maybe I could fix it with something. You have to think. Right, let's define Adeles. So we're really interested in the Adeles. Turns out we're actually interested in the units of this ring. Of AK. Well, we are today. Tomorrow, we're going to be interested in this, right? At some point, that's going to rear its ugly head, because we had GLN of QP, and this is all the GLN of QP's glued together, right? But today, we're going to do global Langlands philosophy for GL1. So let's just talk about this first, and I won't terrify you with GL. I mean, this is already a gigantically huge ring. Taking GLN of it is somehow a little bit beyond. I'm not sure we're ready for it. So let's say we're actually just interested in these things here. These are the units of AK. So now this is one needs to think a little bit about what this space is, right? And also, one needs to think a little bit about the topology on this, because we all discovered in lecture 1, some of us know what this stuff is already, and they know that this has not got the subspace topology. So we have to figure out what the units. Have I still got the definition of the Adeles? No chance. Remember the Adeles, I've got some p-adic, like the Adeles of Q, we've got a p-adic number for all p, but it has to be in ZP for all but finitely many p. But when you have a number like that, if you take, even if all the xp's are non-zero, when you take the reciprocal of them all, you were p-adically integral for all p, but then the problem is that your reciprocal might not be, right? So here's a good example of something not in AK star. So here's a non-example. This thing here, if I define xp to be p, and then x is these xp's, right? That's in the finite Adeles. That's fine, because it's integral. In fact, it's even in the product of p zp, right? It's even in this the easiest part of the finite Adeles. But you can see that 1 over x is in this product of qp's. but it's no good, right? It's non-integral everywhere, right? Well, 1 over x is not in the Adeles. It's not a finite Adele. So we have to be a little bit careful about these units, because it doesn't just mean that, obviously, the Adeles lives in this huge product of p-adic rings, p-adic fields. So for something to be invertible, then definitely all the coordinates have to be non-zero. That's kind of clear, right? All the xp have to be non-zero, but there's something else. There's something, right? All the xp's are non-zero here, but the reciprocal still doesn't work because I have problems at infinitely many primes, you see. So I better make sure that not only the xp is non-zero, but I better make sure that their reciprocals are in zp for all but finitely many p. So for all but finitely many p, I want xp to be in zp, and I want the reciprocal of xp to be in zp, which means I want xp to be in zp star. Okay, so not so hard to check that ak star is the restricted product of kp star, right? And now I have to say what I'm restricting over. So the idea is I'm allowed to be in this for all places P, I'm an element of this, but for all but finitely many places P, I have to have some property that the apostrophe doesn't tell me. So this is terrible notation. So this actually means the xp this is x curly p now, x curly p in product of p kp star such that xp is a unit for almost all p, right? Because if this is really a unit, then there's xp, it's in the Adeles, and there's yp in the Adeles as well, such that xp times yp is 1. And xp has got a bad finite set S, and yp has got a bad finite set T. And if you're not in S and you're not in T, then xp is a p-adic integer, and yp is a p-adic integer, and their product is 1, so they're p-adic units. So there's that must be what the I haven't done this board. I've been here a week and I still haven't quite got the system. Oh, have I? Yeah, sorry, I put a yeah. Yeah, well spotted. I may as well get this right. We can check that AKF star is this, and so while I'm here, see, and hence using the same crappy notation, AK star is the restricted product over all V of KV star, right? Equally. So now V is a finite or an infinite place, right? So sorry, this is KV. These are stars, and this is the dodgy definition of restricted product. So to make this whole, what data do you need to make this apostrophe work? You need a whole bunch of topological spaces, or topological spaces with extra structure, and for all but finitely many of them, you need a special subspace. And then the idea is, for all but finitely many elements, you have to be in the special subspace. And the problem with the apostrophe is it doesn't tell you the special subspace. And for infinite places, there's no special subspace. But there's only finitely many infinite places. So you don't care. This is why S often contains all infinite places. Right. Oh, I was talking about. So now I've kind of defined what AK star is. Let me topologize. Let me just make it quite clear. Topology on the finite Adeles, the finite Adeles. These are called the Adeles. Maybe I should say this, right? Equals the Adeles of K. Sorry, that's the definition. The units of the Adeles are the Adeles. Historically, I think I might have told this story. Historically, Adeles came first. That Adele used to be two words. It used to be ideal element, and it was abbreviated Adele by Chevrolet because he got sick of writing ideal element. And so it became Adele with full stops in, and then it became Adele without the full stops in, and then people realised that it was the units of a ring, and then this ring got this silly name. So the topology on the finite Adeles, you demand that the product, our nice friendly subring, OK P star, is open with the usual topology. right? So I've just topologized this. And as we saw last week, it can be a rather tricky exercise to check that this is not the subspace topology from the finite Adeles. Right. So I think we're ready for global class field theory. Because like the local class field theory story, I can just state the proof. I can just state the conjecture, well, the theorem in this case. I can just state the theorem and not tell you the proof. So this is everything you need to know about global class field theory, hopefully. Well, it's everything I've needed. I guess depending on what you're doing, you might need more. This is everything I've needed to know about global class field theory. So global class field theory. So when we did local fields, I spent a long time really kind of taking apart K. Had an unramified extension and a tonally ramified extension, and there's some pro-P thing. We spent quite a lot of time wrestling with this. And then I said, oh, and there's a maximal abelian extension as well. And we could kind of like carefully look at in the global situation, we're not going to do any of that. Let me just say, we've got gal K bar over K, right? That's, I've got K and I've got K bar here, and there's a Galois group. And this has got this contains a commutator subgroup, gal K bar over K, C, which is the closure of the abstract algebraic commutator subgroup. And then the quotient is abelian, right? Gal K bar over K modulo the normal subgroup gal K bar over K. C is gal K bar over K ab, right? This is the abelianization. So this is the maximal, the biggest Hausdorff abelian quotient. And this is a closed subgroup because I've taken the closure, and so it corresponds to some field K ab, right? So this Galois group here is gal K bar over K ab. Gal K ab over K. So there's the machinery of the fundamental theorem of Galois theory working in the infinite setting. But at the end of the day, you can either think about it in that fancy way, or more prosaically, We've got some number field K, just choose K bar, an algebraic closure containing K. So K, if you want to regard K as a subfield of the complex numbers, that's fine. And then K bar can be all the algebraic numbers in the complex numbers. So when we've chosen our algebraic closure and then define, then K ab is simply the union of K living in L, living in K bar, right? L over K finite Galois, and gal L over K is abelian. So I'm looking at all the extensions of K, which are Galois, finite in Galois, and such that the Galois group happens to be abelian. And I'll take the union of them all, right? I've got the two such things, then their compositum will also be such a thing. We'll also have a abelian Galois group. So we take all of them. So this is an infinite extension, right? E.g. of K is Q, then K ab certainly contains Q zeta n for all n at least 1. Zeta n is e to the 2 pi I over n, right? An explicit nth root of unity. And so K ab certainly contains the union of these things. K ab contains the union of Q zeta n. Right? So it's definitely infinitely big, even for K is Q. It's a tricky theorem. This is an equality, but that's not at all obvious. That's the Kronecker-Weber theorem. But we don't need to know that right now. What I want to tell you, and in fact that's a weird special case, right? I'm about to tell you what gal k ab over k is, right? I'm going to tell you the answer. For there's two, you see, there's two questions you can ask, right? There's a maximally abelian extension. So question one is, what's that Galois group, gal k ab over k? And then the second question you can ask is, actually, what's k ab itself, right? What's the group and what's the field? So class field theory tells you what the group is, okay? Telling you what the field is, that's called explicit class field theory, and it exists for the rationals, because I just told you the answer, and it exists for imaginary quadratic fields, and the answer's got something to do with J invariance of elliptic curves. And for real quadratic fields, it's a completely open, unsolved problem, as far as I know. Yeah, I don't know. People do think about this problem, and there could easily be partial results I'm completely blind to. But I think for a general number, I mean, a little bit, maybe real quadratic fields, you can use Hilbert modular varieties or something. Maybe Shimura tried something. Q cube root of 2. Q cube root of 2, no one has a clue what k ab is. There I can be pretty confident. Q cube root of 2 is the simplest field for which we know nothing. And I think that we don't know what k ab is if k is q cube root of 2. Anyway, here's the theorem. Global class field theory. For local class field theory, I had an R, and it went from the I think the target of the R was the Galois group. So I'm going to go. We've got gal k ab. We don't have to do global Weil groups. You'll be pleased to know. There is a global Weil group, but it turns out that it was. The local Weil group was a subgroup of the local Galois group. The global Weil group surjects onto the global Galois group. It's a totally weird and different situation. So here is R, the global RK. We had local RKs, and I had an isomorphism. This is just a surjection. But I'll tell you what the kernel of this is AK star over K star. So there we go. So maybe I'll make some. So RK, a continuous group homomorphism, right? It's called the global Artin map. It's a continuous group homomorphism, and maybe I should say a little bit about the left-hand side. Maybe I'll just make the observation that the left-hand side makes sense. Recall that K lived in A of K. I'm thirsty. Do I get to drink yet? 15 minutes. K lives in AK, right? So this, because it meant while this weird diagonal embedding, okay, so whatever AK is, it definitely contains a copy of K, and K is a thing which we kind of understand. And so therefore, AK star, this is the elements of this ring which are invertible. Well, here's a subring, and the invertible elements of that subring is clearly K star, right? And so that AK star definitely contains K star. And what I'm suggesting is that we quotient out by it. So this global class field theory map RK cannot possibly be an isomorphism because, so remark, so this is version 1, this RK, but it's not ideal because I really want to tell you what this group is, so I really need to tell you what the kernel of RK is, right? This RK is clearly, RK can't be an isomorphism. Because the right-hand side is profinite. It's a projective limit of finite groups, right? It's like, ZP, or the product over all primes P of ZP. That's how the feeling for the right-hand side. Whereas the left-hand side contains all this real manifold stuff, right? The left-hand side contains K infinity star, right, which is isomorphic to kind of R star to the power of R1 cross C star to the power of R2, where R1 and R2 are these numbers of real and complex embeddings that R1 and R2 are random non-negative integers, and at least one of them is going to be positive. And these are not profinite at all. These are somehow continuous. These are continuous things, and they're going to have to die, right? There's no maps from the reals to a profinite group. There's no continuous maps from a connected thing to a totally... This is the point. It's not that it's profinite. The right-hand side is totally disconnected, which means that if I have a subset of that Galois group which is connected as a topological space, then that subset has one point in it, right? The only connected subsets are the one-point sets. So I've got K infinity star, that lives in... You see, I've taken the units in K infinity. That certainly lives in those global Adeles. So there's a map, right? I can take this K infinity star, embed it into the global Adeles, and then use RK. And now I've got a map from this space here. If I take the connected component, instead of using R star, I use the positive reals, right? I mean, this is worth recording, I guess. Note that K infinity star connected component, so that would be non-canonically isomorphic to the positive reals to the power R1 cross C star to the R2, right? That is a gigantic connected topological space, okay? Must be killed, right? Must be in the kernel of RK. It must be in the kernel because this is connected, because as its image, continuous image of connected is connected, right? As its image is connected, and it's in a totally disconnected group. Okay, so that has to die. So wouldn't it be great if the kernel was equal to that? And I spent years of my adult life believing that that was the kernel, because my advisor told me, and he was wrong. And it's not often that Richard Taylor's wrong, but he was a young man at the time. It's right if K's got no units. It's right in precisely the two cases when we can do explicit class field theory. It's right for the rationals, and it's right for imaginary quadratic fields. But for general number fields, there is an issue with global units that's quite subtle, and I'm not really going to go into. But one thing's absolutely for sure, I've just proved that this guy here must be in the kernel of RK, or strictly speaking, the image of this thing in that quotient must be in the kernel. And the kernel must be closed, right? Because RK is a continuous map, and the identity is closed, so the preimage of the identity, preimage of a closed set is closed. This RK, what do we know about RK? This kernel of RK is closed, right? And it contains the image. Let me just call it, I don't think I really need to talk about this image very much, so let me not think very much about what the notation is going to be. And contains the image CK of K infinity star connected component in AK star over K star. Okay? So as part of the theorem in global class field theory, the kernel of RK is the topological closure. Right, of CK. And it kind of looks quite appealing that CK will be closed, because CK is closed in AK star, and somehow continuous image of a closed set is closed. Is that a theorem? Yeah, I'm not so sure that's true. And so you see, this CK, the image of this closed thing in here, might not be closed. So better take the closure just in case. And then you talk to Florian Herzig, and he shows you an explicit example of a real quadratic field for which this is not closed. So you do have to take the closure. So I'll make some remark. As we'll see, if K is Q, or an imaginary quadratic field, then it turns out that CK is closed, but not in general. Right. great. I've got 5 minutes. I'm going to finish. I need to tell you more about this theorem. I haven't really finished stating the theorem yet. So just as in the local situation, I kind of wrote down various, I don't know, I wrote down, at the minute, this is a bit of a useless thing because I haven't told you any properties of RK. I mean, I've already told you something. I've told you the isomorphism class of gal k ab over k, right? Because now we know that gal k ab over k is isomorphic to this weird quotient here, modulo the closure of this thing here, right? So in some sense, we quote know gal k ab over k, but we don't know anything about the properties of the map RK. So let me just tell you some properties of RK. Properties of RK. One really cool thing is for all p finite places, there's a commuting diagram, right? We've got k star over ak star by rk to gal k ab over k. But you know what? K has got some completion, kv, right? I can look at k. What can I do? I can look at gal kp bar over kp abelianized. That's the thing we kind of looked at in the first week, and that's going to naturally map to there. That you've got to be careful, right? Do you remember I talked about those groups D, those decomposition groups? For a finite Galois extension, I isolated a subgroup which was isomorphic to a local Galois group. But when I did that isolating, I chose a prime of the top above this prime at the bottom. And once you've chosen a prime at the top, we had an explicit subgroup. And if you didn't use that prime at the top and just had a prime at the bottom, then it was only defined up to conjugation. So this local Galois group was a subgroup of the global Galois group, but only up to conjugation. And I'd have to choose a prime of this above this or something, to choose a prime of k ab above p to get this nailed down. But this is abelian. And so this subgroup is defined up to conjugation, so it's defined. So that really is a well-defined map, right? This is well-defined because we're in the abelian case, as all Galois groups are abelian. So normally in Galois theory, things are only defined up to conjugation. So this is a well-defined map here, and of course I've got my local kp star here, and I've got my local rkp. That wasn't quite how I set up. I mean, remember, this was probably a local Weil group when I did local class field theory, but the local Weil group lives in that local Galois group, so there's no problem at all. And this is the obvious map, right? This is just the component. This is the component at P. If I've got some random element x curly p, then I can regard it as an Adele by defining x to be x curly p at p and 1 everywhere else, right? So just to be quite clear, xp gets mapped to 1, 1, 1, xp, 1, 1, dot, 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 right? So this is local component of this. Sorry, that's gone a little bit near to the statement, hasn't it? Whatever. I just feel it's now confusing, right? This map here, xp, goes to 1, 1, 1, xp, 1, 1, dot, dot, dot. So that's cool. This global Artin map is gluing together all these local Artin maps. As a consequence, this global Artin map there's at most one, right? Because I've just told you what this global Artin map does at every finite place somehow. I've told you what this global Artin map must be on some huge subspace of this. I'm pretty darn sure. Yeah. You know this is continuous, and I think I've just defined it on a huge subspace. I think there's at most one global RV. And then there's just some, let me just do the commuting diagrams bit. Let me just say how it behaves for a finite extension. Because just as in the local case, there's secretly a bunch of cohomological properties as well. What class field theory really does for you is it tells you what abelian extensions of local and global fields look like, and it also tells you the cohomology of local and global fields, right? It tells you how to work out all the cohomology groups you might be interested in. It tells you how to work out the cohomology of this guy here. This has an action right? This has an action of, if K was gal R over Q, this has an action of gal K over Q. And one could ask what the cohomology of that is. And all these things are answered by global class field theory. And I won't bore you with all the details, but I think I should just say something about finite extensions. So the thing I have written down here is if L over K is finite, you see then, just as in the local case, gal L bar over L is a subgroup of gal K bar over K. So there's an obvious map from gal L bar over L to gal K bar over K. And now we apply the ab functor, and we get a map from gal L ab over L to gal K ab over K. And I mentioned this in the local case, but let me mention it again now. The map from L bar over L, gal L bar over L to gal K bar over K is injective. But the ab functor doesn't preserve injectivity. I gave an example, right? Just take a cyclic group embedding in a simple group, take the abelianization dies. The abelianization kills the simple group, but not the cyclic group. So this map here might not be an injection, which is good, because when you see what I'm going to write on the right-hand side, you see that no way is this an injection. This is just the norm map again to K star over AK star. So you have to think about what that norm map means, right? But it means something. This is RL, and this is RK. I've written etc, etc, etc. There's another one, right? There's an obvious map from this to this. There's some kind of inclusion from this to this, and that corresponds to this transfer map the other way. I don't think we're ever going to use that. Right. So now I've told you that. After the break, I'm in a position to tell you. I'm going to tell you the global Langlands correspondence for GL1. Which is just kind of dressing up everything I've said in some fancy language. Right? So, yeah, so blah, blah, blah. Langlands has to figure out what to do next, right? So we understand abelian extensions of global fields. How do we understand all extensions? We don't know. We were stuck for years. Langlands came along, said, interpret this picture representation theoretically, and then it's a statement about GL1, change to GLN, and there's Langlands philosophy, right? So that's where we're going. Langland's amazing reinterpretation of this as the statement that some sets are in bijection with each other, plus blah, blah, blah. Exhausted.